goals of Chapter 11 are understand intermolecular forces such as the dipole-dipole moment, dispersion interactions, ion dipole interactions, and a very special type of dipole-dipole interaction, and that is hydrogen bonding. Another goal is to know the four basic properties of liquids. Understand phase changes. So these are changes that occur when a solid goes to a liquid goes to a gas, or a gas goes to a solid, or a gas goes to a liquid, all those different combinations. So one of those changes involves vapor pressure. So understand vapor pressure, delta H vaporization, and delta H fusion. So basically anything that involves phase changes. Know how to use the Clausius-Clapeyron equation that relates the vapor pressure with a temperature. Know and understand how to use the heating cooling curve and be able to recognize a phase diagram. So as an introduction to this chapter, we want to ask ourselves the question, what are some of the forces that holds molecules together? So imagine you have molecule A here in gray, molecule B here in blue, and a molecule here, we'll call it C, and molecule C is in red. So molecules will attract to one another, or they can repel one another. A classic example is oil and water. They have intermolecular forces that repel one another. So forces between unlike molecules, maybe like a water and an oil, they will sort of partition and stay away from one another. Whereas other types of molecules, say for instance, hexane and decane, those molecules, the way their structure is found, they will actually attract to one another. So hexane and decane, or hexane and octane, or perhaps water and salt. They actually attract to one another and they actually get a homogeneous solution. So there's no partitioning, they just join as one. So a bigger theme question is, what are these forces that make a molecule want to be attracted to one another, and in this case form a homogeneous solution? Or what are the intermolecular forces that make molecules want to get away from each other, such as hydrophobicity, or such as oil and water that sort of partition and separate and form two phases? So some of these intermolecular forces that compel two molecules to repel, or compel two molecules or three or four to attract one another, are dispersion forces, which are kind of very weak, and they're always going to be found. So on a test question or an exam question, what intermolecular forces actually exist? You can always write dispersion forces because they're just so weak. They have to do more with electron cloud distribution than how it always circulates. Ionic is a special type of intermolecular interaction. It's very strong, such as your sodium chloride or your calcium chloride. So that's a very strong intermolecular interaction, only because it's a charge transfer. Pluses really are interacting with the minuses. A full plus is interacting with a full negative. And then we want to take some time to talk about dipole-dipole interactions. A special type of dipole-dipole interactions is hydrogen bonding. So if a molecule is polar, it has a region that's net positive, partial positive, and a region that's partial negative, and those partial positives can interact with a partial negative. So that, in essence, is a dipole-dipole interaction between two polar molecules, or even two nonpolar molecules. And we want to classify a special category of dipole-dipole interaction, and that is hydrogen bonding. And then another type of intermolecular force are ion dipole interactions. So this is the reason why sodium chloride dissolves in water, because water solvates the individual ions. So what are the implications of this? So take two molecules here that I've obtained from various websites. One of them is ethanol, CH3CH2OH, and the other one is dimethyl ether, CH3OCH3. So the first thing I'd like for you to realize is that both of these molecules have 2 carbons, 6 hydrogens, and 1 oxygen. And so basically these are 2 isomers of one another, different arrangements of the atom that constitute the molecule. 2 carbons, 6 hydrogens, and 1 oxygen arranged differently. In the ethanol form, look at the dramatic changes in these physical properties. The melting point is minus 114 degrees C for ethanol. And well, there's not much of a difference here, minus 138.5 degrees for dimethyl ether. Really, the stark contrast happens right here at the boiling point. So C2H6O, the ethanol form or the ethanol arrangement, has a boiling point of 78.37 degrees C, whereas the C2H6O arrangement in the form of CH3OCH3 has a boiling point of minus 23 degrees C. So you have stark contrasts in the way the atoms are arranged. Both molecules are C2H6O. The arrangement really changes the boiling point significantly. Chapter 11 deals with intermolecular forces, so we are focusing on forces between molecules, between molecule A and molecule B, not within molecules, which are known as intramolecular forces. So attraction and repulsion is going to be the main theme of this chapter. What constitutes a molecule to quote-unquote like one another, and what constitutes a molecule to quote-unquote dislike or repel one another. Another focus of this chapter is phases. So a phase can be a solid, liquid, and gas that is sort of halfway in between, so sort of demarcates. You have both solid and liquid phases, or you have both liquid and gas phases, or you have both solid and gas phases. So basically you have sort of combination of two of the three states of matter. So we're going to be talking a little bit about that as well. Phases are best typified by what is known as a phase diagram, and phase diagrams are pressure and temperature relationship, particular pressure, any particular temperature, and what is the phase, solid, liquid, or gas. And we studied gases in Chapter 5 in Chemistry 1. Gases diffuse, gases spread out. We will talk a little bit about solids in Chapter 12, but not that extensively. Solids have a density, and they don't spread out like gases. They're very compact. It's hard to compress a solid, whereas you can easily take a piston and compress a gas. So gases are very sensitive to pressure and temperature variations, whereas solids need extreme pressures and extreme temperatures before anything of substance happens to them. Gases just diffuse, so they're all around, they spread out, and solids really are a very lattice-like and very organized structure. So the atoms are oriented in a very specific three-dimensional organization. So lattice-like structures, very organized, is what typifies a solid. And then we kind of tiptoe the line with liquids, because liquids, like a gas, take the shape of their container. Liquids are sensitive to temperature and pressure, not as much as gases and not as much as solids, though, which are sort of don't care about pressure temperature considerations unless it's very, very high or very, very low. So liquids sort of straddle the line. Liquids, their molecular motion is intermediate between a gas, which is free-flowing and diffuse, and a liquid, and a solid, which is compact and fixed. So liquids kind of have it both ways. Forces that we are going to be talking about in somewhat great detail here. One thing that I do want to emphasize is that all of these have differing strengths, and a hydrogen bond comes under the category of a dipole-dipole moment. So this hydrogen bond is a very unique dipole-dipole interaction. And all of these have differing strengths. So let us scroll down and talk about the different strengths. So the strength of intermolecular forces, ionic interactions, are the strongest because they are a full charge that is being interacting. So a full positive interacting with a full negative. And then when you have these partial charges interacting with a partial negative of the same or different molecules, that is when you start getting lower strength compared to ionic. But notice that hydrogen bonding, which is a special type, a special category of dipole-dipole interactions, is stronger than dipole-dipole interactions themselves. So the subcategory is a little bit stronger than the main category. And then the weakest are London dispersion forces, which are universal. They're found everywhere. Also not included in this triangle of strength are ion solvation interactions. Those are pretty strong as well. That is why water can solvate certain ionic compounds. So they're probably going to be in the strength chart probably around here. Not as strong as hydrogen bonds, but maybe along the same strength as a dipole-dipole force. All right, let's talk about dipole-dipole forces. The first thing that you should realize is that we're talking about two polar molecules. So two molecules that have a net dipole moment. We talked towards the end of Chemistry 1 about polarity and how some molecules, mostly molecules that are asymmetric, and most molecules that have electronegative elements, such as oxygen, fluorine is very electronegative, nitrogen, sulfur, these pull electron density towards them, and they pull them away from elements such as carbon or elements such as hydrogen. So the net result is that these types of molecules have a net dipole moment. And in a net dipole moment, the partial negative of one molecule interacts with the partial positive of another molecule. So this is partiality, contrasting that with an ionic interaction, which is a full positive interacting with a full negative. Next, we'll go into ion dipole forces. So as the name implies, we do have the full charge of an ion, full positive or full negative, interacting with the partial charge of the polar molecule. So it could be a partial negative or a partial positive of the polar molecule. So these are pretty strong as well. And the key point is solvation. So if we're going to talk about water specifically as the and its interaction with a full ion, this is the impetus for why some substances dissolve. So in an ion dipole force, here you have the sodium ion, and pretend this is a water molecule. You can imagine the partial negative of the water molecule interacting with the full positive of the sodium cation. And same thing here, iodine, or maybe consider the chloride ion or bromide ion. Here the partial positive of a water molecule is interacting with the full negative of the iodide, chloride, or bromide ion. So solubility and dissolution is really mediated by ion dipole forces. So that's why some substances can dissolve in water. Water sort of solvates these ions, and this is actually shown here. So here's your ion, and water sort of just complexes it. And the key word here is solution. So this is the basis for why we have homogeneous solutions. Also, a lot of this has to do with size interactions. So sodium ion is a pretty big ion based on its position in the periodic table. And so you'd have a weak interaction just due to size. And magnesium ion, by losing 2 electrons, is actually a little bit smaller, and you have a little bit of a stronger interaction. Okay, let's talk about dispersion forces. There's really not much to say about this. These also go by the name of London dispersion forces. Some textbooks call this, I guess, van der Waals, though all these forces can be called van der Waals forces. These are very, very weak, and these are almost universal, meaning that every intermolecular force is going to have dispersion forces. So in an exam, just write dispersion forces, and that will give you the correct answer. However, stronger forces will overwhelm dispersion forces. So what are dispersion forces? Well, as stated before, they will always exist, whether the molecule is nonpolar, whether the molecule is polar, partial positive or partial negative. And it has to do with the facet that electrons that are in the molecule are circulating. So when an electron circulates, it exhibits a temporary dipole moment. And that temporary dipole moment gives a very, very weak and very fleeting interaction between molecules. So we can actually show dispersion forces in this figure. Here is a molecule, and the electron cloud is circulating. And when that electron cloud circulates, you kind of get a cigarette shape. And that partial negative of that circulating, very fleeting electron sort of interacts very weakly with a cation. and this partial circulating electron cloud, where the electron density is sort of away, that part of the molecule becomes partial positive, and that can interact with an anion. But you have to remember that this is very, very weak. It's very, very fleeting. It's very, very temporary, and so it's, even though it's always there, it really has no bearing on your physical properties such as melting point and boiling point. So here you see all the different dipole-induced dipoles as a result of electron circulation. Again, the key point is that very, very weak and very, very temporary, very, very fleeting interactions, and these will always exist no matter what combination of molecules you're talking about. All right, now let's focus on a very important type or category of dipole-dipole interaction, and that is the hydrogen bond. So the hydrogen bond is special because it's between three atoms. Okay, it is between a hydrogen of one molecule with an oxygen of another molecule. So here you see a hydrogen bond. It is also between the nitrogen of one molecule and the hydrogen of another molecule. So notice the molecule can be the same. And so that constitutes one type of hydrogen bond, nitrogen of one molecule with the hydrogen of another, hydrogen of one molecule with an oxygen of the other. The hydrogen bond can also be with different molecules as well. So this is between a hydrogen of one molecule with the oxygen of a second molecule. So basically we have three things that we're talking about here. We're talking about hydrogen and oxygen, hydrogen and nitrogen, and also not shown here is hydrogen and fluorine. Actually, it is shown here, a hydrogen and a fluorine. So let's take a look at this a little bit more keenly. Polar molecule water, this oxygen becomes partial negative due to polarity, and another water molecule, that hydrogen becomes partial positive. So partial positive with a partial negative. Okay, same thing here, nitrogen is partial negative, interacts with the partial positive of another NH3 molecule, ammonia. Here the partial negative of a water interacts with the partial positive of a hydrogen. That is partial positive because the ammonia pulls electron density away from it. Fluorine is the most electronegative element in the periodic table. So fluorine is going to have a very, very strong partial negative, not full negative. It's not an ion. It's going to have a very, very strong partial negative, and that will interact with the partial positive of another molecule that has a hydrogen. In this example, you see here NH3. So notice some commonalities. Notice that you're going to have a hydrogen that participates, hence hydrogen bond, and then an oxygen, nitrogen, or fluorine that participates from the second molecule. And this can go on and on and on along three-dimensional space. So ultimately, molecule 1 can be the same, molecule 2 can be the same, molecule 1 and molecule 2 can be different, and you will still get a hydrogen bond. So really what I tell students is look for a hydrogen on one end of the molecule, look for a fluorine on the other end. Look for an oxygen on one end of the molecule, look at the hydrogen at another molecule end. Look for a nitrogen on one end of the molecule, and look for a hydrogen on another end. So when you do that, you can imagine hydrogen bonding and that just sort of going along in three-dimensional space. These guys are going to be partial positive because this X is pulling electron density this way, away from the hydrogen. And the presence of fluorine, oxygen, and nitrogen, very electronegative elements, are partial negative because they're pulling electron density towards it. You have a very, very powerful effect and a very, very strong effect on your boiling point and your melting point, these sort of physical properties. So some biology professors say the hydrogen bond is weak. And here, as a general chemistry professor, I'm saying the hydrogen bond is strong. This has to do with perspective and context. The hydrogen bond is weak maybe in the cell where you have a lot of covalent molecules, actual bonds, actual pi bonds and actual sigma bonds. But from a chemistry perspective, not a biological perspective, these hydrogen bonds are very, very strong when you compare it to normal polar-polar interactions or normal London dispersions, which are very, very weak in and of itself. Okay, so there's no bonding here. Even though it's called a hydrogen bond, there's no actual sharing of electrons. It's just a very, very strong mutual attraction towards one molecule towards the other. And that is what a hydrogen bond is. So in that regard, a hydrogen bond is very strong. All right, the key for hydrogen bonding, look for these three guys. Look for an OH, so that's called an alcohol functional group. Look for a nitrogen, NH or NH3, sort of that is called the amine or amino functional group. Or just look for the element fluorine attached to another molecule. So let's look at real examples here. So these are organic chemistry compounds. And you don't really need to know what these stick means, but I'll just tell you that these points here represent carbon atoms, and they're fully saturated with hydrogen. N-dimethylethylamine. This has a dipole-dipole interaction. It's just it's just nitrogen with 3 CH3 groups. And here's a CH3. Remember that point, or that end, is carbon fully saturated with hydrogens. This end of carbon has hydrogens. This end and this end are carbons fully saturated with hydrogens. So this nitrogen is electronegative, but there's no potential for a hydrogen bond. The way N-dimethylethylamine will interact with other molecules of itself is through the nitrogen. And so that is a dipole-dipole interaction with itself, and that will have a boiling point of 36 degrees C. Now, when you start having NH2 with the two hydrogens, the N and the H, that's when you start having hydrogen bonding. So again, look for an NH or an OH or simply a fluorine. So this H that's sticking out, one of the H's, can hydrogen bond with one of the N's of another N-butylamine. And notice the change. You have a 40-degree increase in boiling point. So it takes a lot more energy to disrupt those hydrogen bonds because the hydrogen bond is a very strong dipole-dipole interaction. Now look at an ionic compound, tetramethyl ammonium chloride. You have a full positive of this nitrogen with all these 4 CH3 groups and the full negative of the chloride ion. So ionic is the strongest. Remember our triangle of strength. So it's going to take 260 degrees of heat to break apart an ionic bond. So if you talk about strength, nothing exceeds the strength of disrupting an ionic bond. You need a lot of energy to disrupt a hydrogen bond because they're a very strong class of dipole-dipole interaction. You're not going to need as much heat energy to break apart molecules held together strictly by dipole-dipole moments. Right, here's another functional group, the carboxylic acids. And so here you have two oxygens, polar molecule. This would be partial negative here. This will be partial negative here. And you have a dipole-dipole moment. The boiling point is 80 degrees. Once you have the OH group, that hydroxyl group, you have a carboxylic acid. And that OH can hydrogen bond. This H sticking out can hydrogen bond with another O of this molecule. This O right here can hydrogen bond with another H molecule that's found on the end of butyric acid. So the OH is here. It can interact with another H from another molecule, and this has hydrogen bonding. So it takes about 80 degrees more heat energy to disrupt hydrogen bonding. When you have something completely ionic, yes, ionic trumps everything. The full negative of the oxygen, this is called a carboxylate. When you protonate it, it becomes a carboxylic acid. This carboxylate, the full negative, will interact fully with the full charge of sodium. It takes greater than 260 degrees of heat energy to break apart ionic bonds. So, interesting to note here, both of these have the same molecular weight. Go back up here, both of these have the same molecular weight, but the way the atoms are arranged, one can hydrogen bond, one of these can hydrogen bond, and that gives you a dramatic change in your boiling point. It's worth noting, intermolecularly speaking, hydrogen bonding, or a substance that hydrogen bonds, has strong intermolecular forces. So that's an important point. A substance that can hydrogen bond has very strong intermolecular forces. A substance that's held together by dipole-dipole interactions from one molecule to another molecule is strong, but not as strong as a hydrogen bond. Couple of more examples. Here's pentane. Okay, all you have are a bunch of CH3 and CH2 groups, no polarity whatsoever. The boiling point is 36.3 degrees C. Once you add that OH group, the boiling point really shifts. Okay, so what's the difference between the alcohol butan-1-ol or 2-methylpropanol? Okay, the differences in the OH group constitute about 3 to 4 times increase in the boiling point. So we have stronger intermolecular forces in butanol and 2-methylpropanol because of the hydrogen bonding potential provided by the OH group. Right? So strong intermolecular forces here, strong intermolecular forces here, weak intermolecular forces here. What holds together pentane with another pentane molecule? It's nonpolar interactions. So nonpolar interactions here, hydrogen bonding interactions here, and that's why you have such a stronger increase in the boiling point to break the intermolecular forces of the alcohols compared to the alkanes, such as pentane. Okay. So the bottom line in this chapter, in this context, hydrogen bonding is a strong intermolecular force. The most famous example of hydrogen bonding is water. So check out all these different hydrogen bonds, the OH of one molecule interacting with the H of another molecule. So the H of this interacting with the O of that, the H of this interacting with the O of that, the H of this interacting with the O of that. So seeing all those green lines sort of held together in three-dimensional space makes water in the solid state very, very strong. So it's so strong, it takes about 6,000 joules of energy. Remember, the SI unit of energy is joules. It takes about 6,000 joules of energy just to break 1 mole of ice. Okay, 1 mole of ice, which is about 18.01 grams of ice. So 6,000 joules of energy, so that is a lot. And one of those things that make water such a universal solvent, and such a solvent that sort of sustains life. Okay, another interesting property, especially for maintaining aquatic organisms, S is less dense than ice, is less dense than water. So that has implication for why marine life and aquatic life can thrive. So hydrogen bonding network in water, very, very exquisite, makes water lattice-like. What other things have lattice-like arrangements of their atoms? Solids. So this is like a solid, and the arrangement of the atoms represent a solid, a very organized three-dimensional structure. But in every sense of the word, this is a lattice held together by hydrogen bonds, not the typical lattice that we find in solids. So again, an amazing things that these hydrogen bonding within water sort of resemble the intermolecular properties that hold solids together. All right, let's do this practice problem here. Which of the following species are capable of hydrogen bonding amongst themselves? So take a look at this and see if your answer coincides with mine. So the answer to this problem is CH3OH. This molecule is called methanol. And methanol, by virtue of that OH group, can form a hydrogen bond. While this may be a polar molecule, you got to see that you don't have an OH here, you don't have an NH here, and you don't have an F. So this is polar, undoubtedly, but we don't have the three main components that comprise a strong hydrogen bond. So hydrogen sulfide will not hydrogen bond to itself or to another different molecule, and benzene at C6H6 is nonpolar, so there's absolutely no way it can hydrogen bond. How about this practice problem? Which of the following can form hydrogen bond with water? So dimethyl ether, methane, fluorine, formic acid, this is called formic acid, and the sodium ion. All right, so dimethyl ether can form a hydrogen bond with water. The basis for that is the hydrogen has a partial positive. This oxygen has a partial negative. So that's an OH forming a hydrogen bond with an O. And so this can form a hydrogen bond with water. Methane is nonpolar and it will not form a hydrogen bond. Fluorine will not form a hydrogen bond with water because this is a nonpolar molecule. Because it's a nonpolar molecule, there is no net dipole moment. Formic acid, this is a carboxylic acid. This can hydrogen bond with water. The H from the water molecule, or the OH from a water molecule, can interact with an H, this end H on formic acid, so you have a hydrogen bond that extends all throughout the molecule. And sodium ion will not hydrogen bond with water, as sodium ion will undergo what is known as an ion dipole interaction with water, or it will undergo what is known as solvation. Let's take some time to discuss the properties of liquids. So I'm not going to go into incredibly detail here, but these are a couple of things that liquids have. So liquids have a surface tension, which basically means that liquids at the surface have a little bit of a stronger interaction than at the bulk liquid phase. So at that sort of what I will call the air-water interface or air-liquid interface if you are not talking about water, the liquid molecules at the surface that are touching the air or contiguous with the outside environment or touching the gas maybe, they're a little bit more stronger and held together, a little bit more tight. Viscosity has to do with resistance to flow. So some molecules are more viscous than others, and some molecules can just really glob, have a molasses-like consistency. The third and fourth I sort of combined, adhesion and cohesion. So this is responsive for capillary action, water or any liquid being sucked in a little bit, and also giving rise to what is known as a meniscus. So meniscus is really how we measure, the proper way we measure volume. That has to do with the liquid molecule adhesing or cohesing with the glass of your container. The lung is an air-water interface. So at that air-water interface, the molecules that are at that surface are known as lung surfactant, and they help and aid in breathing. So substances such as a lung surfactant sort of lower the surface tension so that the alveoli can expand and contract. So this has a tremendous biological implication, particularly in the lungs, where the breathing unit is the clump of grapes known as the alveoli. But again, at the surface, you're going to have tighter, more stronger intermolecular forces, and that gives rise to surface tension. So you can actually see here, if you look at this figure, you're going to have strong intermolecular forces right here, right where this air, let's call this air, and water, let's call this liquid water, right at the air-water interface, you're going to have surface tension. And water has one of the highest surface tensions of all liquids known. Adhesion and cohesion. So cohesion is molecules that attract between each other, okay, so intermolecular interactions, and adhesion is the attraction with molecules that are unlike. So adhesion gives rise to your what is known as meniscus. You see here some of these water molecules are attracting a little bit more to the glass. Here cohesion, some of these water molecules on the surface are interacting and giving rise to surface tension. All right, viscosity is resistance to flow. friction to flow, and some molecules have higher viscosity than others. So maple syrup is probably our best example for viscous. Molecules that have strong intermolecular forces. So now you should come to the point to one of the themes here, is that strong intermolecular forces means something that has hydrogen bonding potential. So that's going to take a lot of energy to break those apart, right? So another molecule that has a lot of strong intermolecular forces is glycerol. It has 3 OH groups within the molecule. So there's a lot of hydrogen bonding potential there. So we would expect glycerol, which is a main component of antifreeze, we would expect it to be viscous, and real life tells us that glycerol is very viscous in this very weird experiment known as the Thomas Pernell experiment. So this is probably the most viscous man-made substance. It was made in the 1900s or so, and there's a webcam where they're looking for the 10th drop to come out. So I think the 9th drop came in 2013, but this is a very extreme example of liquid and the property of viscosity. Here's a table of viscosity. Viscosity is temperature dependent, so a lot of these items are going to be dependent and quoted at a specific temperature. And I'm not going to concern myself with the units of viscosity, but I'm bringing your attention to water, 1.01 times 10 to the minus 3, and compare that with glycerol. So what you see here are different molecules, and I want to bring your attention to the fact that glycerol, though you don't know the structure, you're just given the molecular formula here, or empirical formula here. Glycerol actually has 3 OH groups in the arrangement, and it has a very, very high viscosity. Okay, ethanol, you see that OH group there, okay, pretty high viscosity. Diethyl ether or ether, okay, this is the same thing as dimethyl ether, but now we have ethyl group, so this is diethyl ether. That oxygen can form potentially a hydrogen bond, or that oxygen can form a polar bond with another polar part of the molecule. So diethyl ether will have dipole-dipole with another molecule of itself. So not as strong as ethanol. So diethyl ether has 10 times less viscosity. Okay. Carbon tetrachloride, it's a nonpolar molecule, no hydrogen bonding. It does not have as much viscosity, so it's kind of low, especially when compared to diethyl ether. And then benzene. Okay, benzene has viscosity that's kind of low, but benzene has what's known as pi-pi stacking, aromaticity. These rings of benzene can actually stack upon one another, and that actually counts. So going from a liquid to a gas is known as vaporization. Okay, the energy required to have 1 mole of a liquid go to 1 mole of a gas is called the delta H of vaporization, okay, also known as molar heat of vaporization. So liquid to gas is vaporization. If we want to go the other way, it's called condensation. Going from a solid to a liquid is known as melting. Now, going from a solid to a liquid is going to require energy, and that energy is not the delta H of vaporization, but we call it the delta H of fusion, okay, molar enthalpy of fusion. And then going from a solid to a gas is known as sublimation. And the reverse process of going from a gas to a solid is known as deposition. Okay? So these can go back and forth. Okay? If you're going forward, you're probably adding energy. If you're going backwards, you're probably releasing energy. Right, liquid to a gas is called vaporization. Some textbooks also call it evaporation. So this is a situation that sets up a variable known as vapor pressure, which is going to be very important in this class. Vapor pressure actually involves a pressure that's exerted on the surface of a liquid. So in order to establish a vapor pressure, you need 2 things. Number 1, you need the liquid to break free at the surface and form a gas. And what will gas do? They will exert a pressure. And where will they exert the pressure? They will exert the pressure back at the liquid. Now, some gas molecules won't just exert a pressure back down at the liquid, they'll actually transform back and undergo a phase change to a liquid. So this is the dynamic equilibrium that we're talking about here. We're talking about going from a liquid to a gas exerting a pressure back down on the surface of the liquid and becoming a liquid itself. So we have this back and forth phase change, liquid to a gas to a liquid. So that is vapor pressure. It is a pressure, it is exerted on the surface of the liquid, but before it gets exerted, the molecule must become a vapor. Right? So delta H of vaporization is the energy to vaporize 1 mole, or the energy required to take 1 mole of a liquid, convert it to 1 mole of a gas. Now, locally acting gases are called vapors. Okay, so if the gas just spreads out, it's a gas. But if it will exert a pressure back down on a liquid, it's called a vapor pressure. We're talking about 1 mole of a substance. Okay, so this delta H of vaporization is a constant, but the constant is for 1 mole. That's what you look up in a table. So if you have something that's held together by hydrogen bonds like water or like ethanol, it's going to be very hard to break free, quote unquote, into a gas. And because it's harder to break free into a gas, subsequently it's going to be harder to come back into the liquid form and exert a vapor pressure. Okay, so how easy the substance can form a gas depends on the strength of the intermolecular forces. If the intermolecular forces are very weak, the liquid can break free, form a gas, and that gas can locally act on that surface, exert a vapor pressure, and come back down as a liquid. So that is a vapor pressure. Strong intermolecular forces means that you will have a lower vapor pressure. Strong intermolecular forces mean you will have a higher delta H of vaporization. So the more intermolecular forces they are, the higher the delta H of vaporization. I will also add, as another important point, because people get this confused a lot, is that the lower the vapor pressure will be exerted. So this is another critical point. Higher energy required to vaporize it because you have strong intermolecular forces like a hydrogen bond. If a molecule is held together by hydrogen bond, it's less likely to break free, quote unquote, to form a gas, which in turn can exert a vapor pressure on the liquid. So higher the delta H vaporization, the energy required to vaporize 1 mole of the substance, the lower the vapor pressure that will actually be exerted. So let's take a look at molar heats of vaporization, delta H vaporization. All right, so here we have benzene held together by nonpolar interactions. Okay, very low delta H vaporization relative to the other guys. Ethanol, that OH, hydrogen bonding, 39,300 joules it requires of energy to break up 1 mole of ethanol, to vaporize it, make it form a vapor. All right. Methane held together by nonpolar interactions by London dispersion forces, 9.2, very, very less. Water, hydrogen bonding network, it takes 41,000 joules of energy to break apart and vaporize 1 mole of water. All right, so higher the delta H of vaporization, I think this kind of makes intuitive sense, the higher the boiling point. Okay, so it's going to take more energy to break apart those hydrogen bonds if you have stronger intermolecular forces. All right, another important point, vapor pressure is going to be quoted at a specific temperature. Okay, so here the vapor pressure depends on your temperature. Okay, it kind of has this, looks like one of those log or natural log curves. Your natural log of P over your temperature is, or your natural log of P over your 1 over temperature is linear. So you can actually do a linear transformation from the right-hand graph to the left-hand graph to get a line. When your vapor pressure is 1 atmosphere, that is your boiling point. It's called the normal boiling point because normal means at 1 atmosphere. Okay, so the normal boiling point at 1 atmosphere for diethyl ether is 34.6. The normal normal boiling point at 1 atmosphere of pressure for water is 100 degrees. For mercury, it's about 357 degrees. So All right, the Clausius-Clapeyron equation equates vapor pressure at temperature 1 to a new vapor pressure at temperature 2. May be worth revisiting. Higher the vapor pressure due to higher temperature. In other words, increase the temperature, increase the vapor pressure, more molecules will break free and then come back down and establish that dynamic equilibrium. So this is the pressure-temperature relationship. Again, vapor pressure is always quoted at a specific temperature. Vapor pressure is always quoted at a specific temperature. So here's the Clausius-Clapeyron equation. Couple of points here. You want to convert your delta H of vaporization to joules per mole. And R here is 8.314 joules per mole Kelvin. And the third point is please, please, please convert your temperatures to Kelvin. And another point I'd like to make is your pressures can be in any unit. Don't feel like you need to convert it to atmospheres or millimeters of mercury. As long as the units are the same between P1 and P2, you can keep the units at whatever the problem tells you the units are for pressure. And another math thing I want to tell you is usually things that are in the natural log brackets don't have units. That's just a rule of math. So what we usually do is we remove the units. And then put the units back. That really has no bearing on whether you get the right or wrong answer, but I'm just saying, historically, natural log, you can't take a natural log of a number with units. You just take the natural log of a number. All right, so let's do this problem here. The vapor pressure of ethanol is 100 millimeters of mercury at 34.9 degrees C. Again, vapor pressure quoted at specific temperature. T1, VP1. What is the vapor pressure at VP2, 63.5 degrees C? And the vapor pressure for ethanol, the energy required to vaporize 1 mole of ethanol is about 39,300 joules. So this is a plug into the Clausius-Clapeyron equation and making sure you know how to do and manipulate the natural log. So take a moment and do the problem and see if your answer matches with. So I just plugged everything back in here. P1 is 100 millimeters of mercury. I notice I removed the units. I converted the delta H of vaporization to joules per mole. So here's my joules per mole, 39,300. My R is 8.314 joules per mole Kelvin. The mole per Kelvin on this denominator flip up to the numerator. Times T1 minus T2. I made an effort to make sure my temperatures were in Kelvin. The Kelvin cancels out with this Kelvin. The joules cancels out with this joule. The moles cancels out with this mole. So I don't have any units, which makes sense because you can't take the natural log of something and have it spit out units. So I computed all of this as one entity on my calculator. And you may want to check my calculations because sometimes I do make mistakes. As an answer for this whole thing, I got minus 1.304. And that has to equal to the natural log of 100 over P2. The task is to just isolate the P2. So the way you isolate the P2 is you take the E of both sides of the equation. E is the inverse of the natural log. So if I take E to the natural log of this thing, it pops it out. It pops the thing out. And I got to take E out of the other side of the equation as well. So doing E exponent minus 1.304, I'm getting 0.2714. I solve for P2, and I get an answer of 368.4 millimeters of mercury. So you raise the temperature to 63.5 degrees C. The vapor pressure increases from 100 millimeters of mercury to 368.4 millimeters of mercury. That actually makes sense. Okay, raise the temperature, molecules dance more, you break free from the boundary, more molecules become vapor. Those vapors can come back into liquid. The dynamic equilibrium is accelerated as you increase the temperature. All right, let's define some terms here. Here we have the critical temperature, the temperature at which a vapor cannot be liquefied. So for water that is greater than 374 degrees C, every liquid substance has their own critical temperature. So above this, you cannot get the water to become liquid, no matter what you do to the pressure. And critical pressure is the pressure required to liquefy a substance at its critical temperature. So for water, this is 217.7 atmospheres. So below this pressure, water will exist as a liquid. Above this pressure, water cannot be a liquid anymore. It just will be a vapor. So here's a phase diagram. It is a combination of pressure and temperature. So temperature is on the x-axis, pressure is on the y-axis. So your xy coordinate is a combination of pressures and temperatures. So I don't know what substance this is, but every substance will have a phase diagram where it can be a solid at a particular pressure and temperature combination, a liquid at a particular pressure temperature combination, or a gas at a particular pressure temperature combination. But then you have pressure temperature combinations where it kind of tiptoes. Okay, here it tiptoes between liquid and a gas. Here pressure temperature combinations along this line tiptoe between being a solid and a liquid. Here you have all three phases, solid, liquid, and gas. And so your critical pressures, notice your pressures in units of bar. And so not millimeters of mercury or atmosphere that we are accustomed to. So here you have your critical pressure. So, all right, we talked about vaporization. Remember, delta H of vaporization required to take 1 mole of a substance and make it into a vapor, and that establishes a vapor pressure. Stronger intermolecular forces lower the vapor pressure, higher the delta H of vaporization. So let's talk about melting. So here are a couple of substances here and their melting points. Again, notice the structure and the type of intermolecular forces. So benzene, pi bond stacking, takes 10,900 joules to melt 1 mole of the substance. Diethyl ether, dipole-dipole interactions, polar bonds, hold these molecules together, takes 6,900 joules of energy to melt 1 mole of the substance. Ethanol, hydrogen bonding, 7,000 or so a little bit higher, right, to melt 1 mole of ethanol, okay, taking it from the liquid phase to taking it from the solid phase to the liquid phase. Dispersion forces, a very, very low amount to melt, and in water it takes a lot to melt relative to all the other guys. Water has hydrogen bonding and about 6,000 joules for 1 mole of the substance. Let's compare the delta H of fusion, okay, molar heat of fusion converting from a solid to a liquid, shown here at the bottom. Delta H vaporization, the molar heat of vaporization is converting a liquid to a vapor. We add these two together, the liquids on one side of the reaction cancel with the liquid on the other side of the reaction, and then the net equation is solid going to vapor. And when you add two reactions, you add their delta H's. So the delta H of sublimation, which is a solid going to a vapor or a solid going to a gas, is your delta H of vaporization plus your delta H of fusion. So we have a relationship between molar heat of vaporization and molar heat of fusion. This is the relationship which we derived above here utilizing Hess's law. A couple of other things to end this chapter. This is called the heating curve, but heating curve happens if you're going from left to right, or if you're going diagonally this way, then it's a heating curve. But if you're going diagonally downward, or if you're going from right to left, you're actually having a cooling curve. So this is actually a combination of a heating curve and a cooling curve. So first, let's note the axes. On the y-axis, you have temperature on this curve, and on the x-axis, you have time. So what happens to a substance if you heat it, or what happens to a substance as you cool it? Let's take the example of what happens to a substance when you heat it, all right? So let's start out at minus 20 degrees C, and let's pretend this is water because everyone is very comfortable and knows what happens to water as you heat it because it's an everyday substance. So let's pretend this is minus 20 degrees C. And over time, we add temperature. So as we slowly ramp up the temperature, we reach a very important point, 0 degrees C. right at 0 degrees C, as we continually add heat and as we continually increase the temperature, notice what's happening here. Okay, over time, your temperature sort of lags. Okay, the reason why it lags is because you are overcoming delta H of fusion. Okay, so this is what we call from A to B a phase change. So here we have both solid phase and liquid phase from A to B. Up to a particular point where all the solid has been converted to all molecules of liquid, the temperature now begins to rise because you overcame that lag. You've successfully overcome that phase change. Now, because I said this example is water, the delta H of fusion of water for 1 mole of water, we can look it up above, and we found that it's about 6,000 or so joules per mole. So we actually can put delta H of fusion here as about 6,000. Once we overcome that and the temperature continues to rise, notice it's no longer lagging. It rises and rises and rises up to point C. Okay, point C is a special temperature. Is going to be 100 degrees C. And at 100 degrees C, you have what is known as the boiling point. Right? So as you continually ramp up the temperature at point C, you notice that you have a time lag here. The reason why you have a time lag is because right here from C to D, you have a combination of both phases. You have a combination of the liquid phase and you have a combination of the vapor phase. Remember, vapor is just a gas molecule that acts locally on the surface. And then you get to point D where all the liquid molecules become vapor. And then as you increase the temperature, you overcome the lag and everything becomes the vapor phase. So that is a heating curve going by increasing the temperature. Now, if we decrease the temperature, it becomes a cooling curve and everything sort of becomes the opposite. So let's do a practice problem here. Calculate the heat released. So heat released when we're going from 124 degrees C to 45 degrees C of water. And so heat released, and we're going from 124 degrees C to 45 degrees C. So we're actually cooling. So this is a cooling curve, not a heating curve. But it doesn't matter because heat released means that our end heat is going to be negative. In order to solve this problem, you're going to need some constants. So I've already quoted here some constants. These are called specific heat constants for steam, water in the steam state, water in the liquid state, and water in the ice state. So go ahead and do this problem and see if your answer coincides with mine. So the trick to this problem is to split this up. So you're going to go from 124 degrees C to 100 degrees C. That's where you have your phase change. So Q equals mc delta T. Phase 1, you have 68 grams of steam. The specific heat of steam is this value that I got from the textbook. And final is 100 minus 124 degrees C is your initial. And solving for that, our units cancel. Minus 3312 joules. Minus sign because heat is being released. And I stopped at 100 because at step 2, as I'm cooling, I have to overcome the phase change, all right? And the phase change here is going from a water that's vapor to water that's liquid. So at 100 degrees, I overcome the phase change, and that is 40,790 joules per mole. So I have to count, this is for 1 mole, I got 68 grams of water, so I got to convert it to moles, and then realizing for every 1 mole of water, it takes 40,790 joules to vaporize it. So it's 154,009 joules to overcome that phase change. And I have to put a negative sign here because heat is being released. We're doing cooling here. And then finally, my third step is to go from 100 degrees C, now I've overcome my phase change, to 45 degrees C. And here water is a liquid at 45 degrees C. So I'm going to use my Q equals mc delta T. I have my specific heat of water in the liquid state. My final is 45 degrees C. My initial is 100 degrees C. all the units cancel out, and my units here are minus 15,630. So adding up all the heats from step 1, this is minus 124 to 100. This is the heat from the phase change, which was a constant. And then this is the heat going from 100 to 45 degrees. And adding all those up, I get a minus 172. The water's cooled from 124 degrees C to maybe minus 10 degrees C. Okay, there I got to account for two phase changes, C, D, and A, B. All right, finally, we're talking about phase diagrams here. We alluded to this a little bit above. These are pressure-temperature combinations. And a couple of points here. Our triple point, solids, liquids, and gases stay together. Okay, so for water, which is shown on the left, the triple point is 0.006 atmospheres and 0.01 degrees C. So if you can get that pressure and temperature combination, you have solid, liquid, and gas water all coexisting together. This is carbon dioxide shown on the right. That triple point is a pressure-temperature combination of 5.2 atmospheres at minus 57 degrees C. So that is where solid, liquid, and vapor or gas coexist. So here I'm using vapor and gas interchangeably. Vapor is just, one thing I want to bring your attention is this slant. Okay, so another property of water stems from the phase diagram having this strange slant between the solid-liquid demarcation. All right, this means that if you actually raise the pressure, okay, of a gas molecule, it's tantamount to lowering the temperature. Or on the flip side, if you lower the temperature of water, okay, you're actually, if I lower the temperature of water, okay, my pressure is actually sort of taking this trajectory. Okay, so that makes water very strange, okay, because of that that negative slant. Normal substances follow carbon dioxide or other substances such as ethanol. They have the slant sort of as a positive slope.